So I want to now go through the idea of a superposition state. So this is our infinite well, and I have written out a specific wave function and then drawn what that wave function looks like. So quick check. This is basically algebra practice. When we look at this, I've actually drawn kind of the v equals 0 line to be my psi equals 0 line. I could have drawn that higher up, that's okay. So I've noted where psi equals 0 is. So note that I have a 0 here, here, and here. So let's look at the functional form and verify that. Well, when x equals 0, this is 0, so the whole thing is 0. Good. When x equals L, this term is 0, so the whole thing is 0. Good. When x is L over 2, this term becomes 0, so I again have a 0 point. So otherwise, getting the form, you could plot it using your favorite plotting tool. So the question is, if this is our wave function, and I said, what's the energy that I measure, how would we go about doing that? Well, recognize that this is not an energy eigenstate, right? Our energy eigenstates, and I'm going to use that phi term, so phi is equal to 2 over L, and then sine n pi x over L, and that's again the notation we would use for these boundary conditions. So going back up here, what's n? N is just a normalization coefficient. So how would you find it? Well, we would basically take this and say if I integrate from negative infinity to infinity, but of course it's going to become, in this case, just 0 to L of psi star psi, which obviously since this is real, this would just basically be this squared dx. This is going to be a terrible polynomial, right? It's doable, but it's kind of terrible. So note that you would maybe want to multiply this out to begin with so that then you're just integrating a polynomial. Not by any means the worst function we're ever going to see. So the key is we would find it this way. You would get what your normalization coefficient is. So how do we go about measuring energy? These are energy eigenstates. That's not what we have. But we would still have an energy. And the reason why it's invaluable to talk about energy is remember that our time evolution is always given by that EI energy term, right? That energy is always in the exponent there. So what we need to do is think about this as an expansion of a sum of energy eigenstates, right? And so we've already seen different wave functions that are explicitly superposition states, right? So for instance, 1 over square root of 2 spin up plus 1 over square root of 2 spin down. Superposition state, easy. Here what's confusing is you don't clearly see that it's a superposition state. But since it is not an energy eigenstate, we can still express it as a superposition of those. So what that would look like is a sum over n, and remember that n starts at 1 and goes to infinity, of Cn, some coefficients. I'm not saying what they are yet, but each one is going to be different, which is why I'm writing it that way. Phi n of x. Okay, not too bad. So we can take whatever general state we want, and we can express it as a superposition. So if we wanted to get the probability of measuring a given energy En, that's going to relate to these Cn's. So the question we want to then ask and answer mathematically is how do we find the value of Cn's given this? So this is where it gets a little bit messy. And I want to make sure I'm following my notes. Let's go back and again think about the idea of bracketing, right? So when I write it this way, I'm in the position representation, but I can move back to thinking just about kets. And so when I express this as kets, I can now rewrite this as, again, that sum, my C sub n, and then I'm just going to call this I'll write it this way, my ket states associated with those, right? So now imagine doing a bracket, right? When we have this, that would look like first your sum, and now this needs to be star, and you would have your phi n bra, and then you would have your Cn phi n cat. Okay, so we know this. We know that this has to equal 1, right? And that would give us a condition. We would only, and let me actually make one change here. What's dangerous when I've written it this way is that I have ends here and ends here. These are actually different sums. So instead, it would be better to, for instance, write this as sub m. And then we could start to put them together, and there would basically be a delta that we get here when m is equal to n. Okay? So this is one way to think about it. But then another is to say, hey, well, I can move this back to the position representation, and that's where you get some integrals. So the caveat is going to be going through and saying that we're going to get these integrals. And in particular, we can then kind of take one of these out and have this relate back to our size. So I've run out of space on the board. I'm gonna have to start a new video to actually do this out, but I'm trying to give you a preview of where we're going. You know, where we're going with this is trying to actually get these values of C. And what it's going to effectively come down to is a relationship between psi and our energy eigenstates. And there's going to be an integral involved. If you've seen a Fourier transform before, we're not quite to a Fourier transform per se, but it's going to look mathematically like there's some similarities. So in a separate video, I'll really go through and follow the rest of this. So we'll come back to this form eventually, but the key is that we have to find these C sub n values.